fiber-reinforced foam concrete. If this was just a regular piece of foam concrete, it crumbled reasonably well. But if I add PVA or PP fibers to it, it BNDs, but does intrigue. 8 minutes to tell you the principle behind this. Summed up in one sentence. The fibers are not hardening. They are sewing foam concrete. 90% air bubbles and 10% cement paste. The bubbles make it light and make it brittle. 1. Thin pore wall, like an eggshell when subjected to force, cracked when pressed. 2. Micro cracks, cement hydration contraction. Internal tensile stress has no place to release. Directly fried cracks. The result is compressive OK. Tensile and flexural resistance is almost zero. Fiber in. It's not rebar. It's stitching. We take PVA polyvinyl alcohol, or PP polypropylene fibers, cut them into small sections of 6 to 12 millimeters, and mix them into the pulp. They don't come to carry the load, but to patch it up. Keywords: bridging crack resistance, energy consumption. 3 reinforcement principles dismantled. 1. Bridge cracks. As soon as the crack appears, the fibers straddle the ends and borrow the tensile force. PVA has a large number of hydroxyl groups on its molecular chain, which form hydrogen bonds with the cement matrix and stick firmly. PP, although hydrophobic, can mechanically bite when the surface is treated with indentations or coatings. Multi-seam cracking gives energy consumption when there are no fibers. A crack goes right through and is instantly brittle. With fibers, the cracks are strung into many thin strips, each draining a bit of energy, which macroscopically manifests as increased toughness. PVA has a higher modulus of elasticity than PP and pulls early on. PP has a high elongation and drags later on. Shrinkage, crack suppression, cement rinks in volume during hydration, and internal tensile stresses are concentrated. The fibers are randomly distributed, like countless rubber bands, to equalize the shrinkage stress to every cubic centimeter and reduce early cracking. PVA versus PP. Who is better for foam concrete? PVA, hydrophilic high bonding. Modulus of elasticity approximately equals 30 GPa, works early, but expensive 23 OK per ton. PP, hydrophobic low bonding. Modulus of elasticity approximately equals 3 GPa. Needs surface treatment. Cheap, under 1 OK per ton. Conclusion: for high strength and toughness, go for PVA. For low cost just enough, go for PP. Budget: you can mix 1-to-1 ratio early on PVA, later on PP. Dosage length dispersion. 3 keys to practice. 1. Add mixture. 0.1% to 0.3% volume fraction is the safest. Any more, the slurry becomes sticky and the air bubbles are hard to stabilize. 2. Length. 6 millimeters for low density below 400 kilograms per cubic meter. 12 millimeters for high density. If it is too long, it will be knotted, and if it is too short, it will not be able to be bridged. 3. Dispersion. Dry mix the fiber first. 3. Dispersion. First, dry mix fiber and cement, then add water, and finally, foam. The order is wrong. The fiber clumping directly into the hedgehog. Common misconceptions corrected. Myth 1. The more fiber, the stronger resistance. Excess equals decreased ease of use, bubble bursting, and reverse strength loss. Myth 2. Fiber equals steel. Wrong. It only improves toughness. Compressive strength is almost unchanged. Myth 3. PP fiber must be worse than PVA. Wrong. In alkaline environments, PP resists aging rather better. PVA PP fiber in foam concrete is like a bulletproof vest. It doesn't add weight, but makes cracks inch away. It is not the main character, but the supporting role to make the main character live longer.